Right now, while you're reading these words, a machine that should have died in 1981 is still awake, still transmitting, still doing something that shouldn't be possible. Its name is Voyager 1, and NASA has just confirmed a finding about it that scientists are describing, in the actual language of a peer-reviewed paper, as impossible. It's not a new telescope, it's not a billion-dollar orbiter, it's a spacecraft the size of a small car, running on less computing power than the key fob in your pocket, sitting more than 15 billion miles from where you are right now. Impossible is a word scientists almost never use. They say anomalous. They say requires further study. They do not stand in front of hard data and call it impossible. But that's exactly the word now attached to what Voyager 1 just sent back. And once you understand what it found, you'll understand why the word fits. Here's the part almost nobody outside a small circle of physicists is talking about. This isn't just a story about an old spacecraft doing something strange in the dark. It's a story about the boundary that protects every living thing on this planet, and what we just learned about it doesn't match anything we assumed. Stay with me, because by the end of this, the sky over your head is going to look a little different. I'm John, and this is your channel. If stories like this are the reason you're here, subscribe now, because we are just getting started. Let's go back to where this all began. September 5th, 1977, a rocket lifts off from Kennedy Space Center carrying a spacecraft called Voyager 1. The mission is modest on paper. Fly past Jupiter, fly past Saturn, take some pictures, gather some data, and then drift off into the dark and go quiet. NASA's own internal planning documents expected the mission to wrap up somewhere around 1981, maybe 1982. A nice little 4-year postcard from the outer solar system, and then silence. That is not what happened. Voyager 1 flew past Jupiter in 1979 and sent back the first close-up photographs of that planet that human eyes had ever seen. It flew past Saturn in 1980, slingshotting off the planet's gravity to pick up even more speed, more distance, more reach. By the end of the 1980s, it had already traveled farther from Earth than anything our species had ever built or launched, and it was still transmitting, still working, still sending its thin signal back across a gap that kept growing wider every single day. Then, in 2012, 35 years after launch, it did something no human-made object had ever done before. It crossed the heliopause. If you've never heard that word, here's what it means, and why it matters more than almost anything else in this story. Our sun doesn't just give off light and heat. It constantly releases a stream of charged particles called the solar wind, and that wind blows outward in every direction, forming a massive protective bubble around our entire solar system. Every planet, every moon, every spacecraft we've ever launched, every living thing that has ever drawn a breath exists inside that bubble. The outer edge of it, the point where the solar wind finally runs out of strength and gets pushed back by the pressure of interstellar space on the other side, that edge is the heliopause. It is the actual physical boundary of everything we call home. In 2012, Voyager 1 crossed through that boundary and kept going. It became the first thing built by human hands to leave the solar system entirely. Not a metaphor, not a technicality, an actual object, launched by actual engineers, now sitting in the actual space between stars. And it kept transmitting. Think about what that really means. Right now, there is a living instrument sitting in interstellar space, not orbiting a planet, not floating near the edge of our system. Actually, inside the region that separates our star from every other star, a region no telescope, no simulation, no theoretical model has ever been able to observe from the inside, because nothing we ever built had made it that far, and what it started sending back was not what anyone expected. Here's where it gets strange. For decades before Voyager 1 got there, physicists built detailed models predicting what interstellar space should be like. These weren't guesses. They were rigorously tested, peer-reviewed frameworks built by some of the sharpest minds in physics, and they all told roughly the same story. Interstellar space should be quiet, cold, sparse, a kind of slow, dim waiting room between star systems, where particles drift lazily and not much happens. Voyager 1 walked into that waiting room and found a storm. Starting in 2017, the plasma wave instrument on board began picking up something nobody had predicted, and nobody could immediately explain: a persistent, narrow-band hum in the fabric of interstellar plasma. Not a one-time spike, not a glitch that could be waved away, a continuous signal present year after year detected across a stretch of space stretching more than 900 million miles. For comparison, the distance from Earth to the Sun is 93 million miles. This hum has now been tracked across a region 10 times wider than the gap between our planet and our own star. When researchers finally published their findings, the language was unusually direct for a scientific paper. Interstellar space, they concluded, is not the smooth, uniform void the models described. It is turbulent. It has structure at every scale, from distances you could measure in meters to distances measured in millions of miles. It behaves, in a very real physical sense, like something alive with motion. And we had simply never known it because we had never had an instrument sitting inside it before. Sit with that for a second. Every model of the universe beyond our solar system was built from the outside, from a planet, using telescopes and math and theory. And the first instrument we ever actually placed inside interstellar space is now telling us that those models missed something fundamental, that the space beyond our home is stranger, more active, and more structured than anyone predicted. But here's where this stops being an abstract physics story and starts being personal. Because the heliopause, the same boundary Voyager 1 crossed, isn't just a line on a diagram. It's a shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles that come screaming in from distant exploded stars, and keeps them from reaching the inner solar system at full force. If that shield behaves differently than we assumed, if the environment pressing against it from the outside is more violent and more unpredictable than any model accounted for, the questions that raises about long-term life on Earth are not small ones. And what NASA has now confirmed is that the environment pressing against that shield is exactly that. More turbulent, more energetic, and more chaotic than anything in our physics textbooks described. Here's the detail that turned this from a strange curiosity into something researchers are calling genuinely impossible. The leading models had always predicted that crossing the heliopause should feel gradual, slow. The solar wind thinning out on one side, the interstellar medium slowly becoming detectable on the other, the two blending together the way a river gently meets the sea. That is not remotely what Voyager 1 found. At the heliopause, particles weren't drifting calmly from one environment to another. They were slamming into each other at speeds approaching a meaningful fraction of the speed of light, generating temperatures approaching 30,000 degrees Celsius, not inside a star. At the outer edge of our own solar system, in a region that was supposed to be cold and mostly empty, some of the scientists studying this data have started calling it, without exaggeration, a wall of fire, a genuine concentration of ultra-energetic charged particles forming a physical barrier at the edge of everything we call home. And then came the finding that made physicists start using the word impossible out loud. For decades, one of the foundational assumptions about the heliopause was that it should mark a clean separation between two completely different magnetic environments. The sun's magnetic field on the inside, the galaxy's own separate magnetic field on the outside. Two distinct systems, cleanly divided at the boundary, the way a property line divides two neighboring yards. Voyager 1 found something else entirely. The magnetic field lines on both sides of the boundary weren't separate at all. They were connected, linked through a process called magnetic reconnection, where field lines from two completely different sources meet, rearrange themselves, and release energy in the process. Our solar system and the galaxy surrounding it are not magnetically isolated from each other. They are actively, physically linked, exchanging energy at the exact boundary that was supposed to keep them apart. This isn't a footnote, and it isn't a minor correction to existing theory. If the relationship between our solar system and the wider galaxy is this dynamic, this connected, this energetic, then the fundamental question of how the heliosphere has protected life on Earth over geological timescales needs to be reconsidered from the ground up. That is the sentence that made this go from an interesting anomaly to something NASA-affiliated researchers describe, carefully as forcing a rewrite of the textbook. Before we get to what's happening right now in 2026, you need to understand how close we came to never learning any of this at all. Voyager 1 nearly died in 2023. For 5 months, the spacecraft kept transmitting a signal, but what it was sending back was gibberish, corrupted code, scrambled data that engineers at NASA's Jet Propulsion Laboratory, after nearly 5 decades of reading everything this spacecraft had ever sent, simply could not decode. The signal was there. The instrument was alive. But whatever it was trying to say had become unreadable static. The cause, when they finally traced it, was almost absurdly small and devastating at the same time. A single memory chip inside the spacecraft's flight data system had physically deteriorated after nearly 5 decades of constant exposure to cosmic radiation. One tiny piece of 1970s hardware, a fraction of an inch across, had quietly failed, corrupting the exact section of software responsible for formatting and transmitting scientific data. No alarm went off, no warning was sent. It just failed silently after 46 years of non-stop operation in the harshest environment any human-made object has ever endured. Fixing a broken part normally means going to where it is and swapping it out. That option didn't exist here. The broken component was 15 billion miles away, unreachable by any form of transportation that exists, with no repair mission possible on any time frame that would matter. The only tool available was a radio, signal traveling at the speed of light, and even that took 22 hours just to reach the spacecraft. 22 hours out, 22 hours back, 44 hours minimum for a single round of communication. Picture what that actually looked like from inside mission control. You study a piece of corrupted data. You form a theory about what might be wrong. You write a set of instructions to test that theory. You transmit it. You wait 22 hours. You receive whatever comes back. You analyze it. You discover it's slightly different from what you expected. You form a new theory. You write new instructions. You wait 22 hours again. You repeat this patiently, methodically, for months, knowing the entire time that a single wrong command sent across 15 billion miles of empty space could end the mission permanently, with no chance to try again. The team at JPL did this for months, and they succeeded. They figured out the corrupted code couldn't be repaired, but it could be relocated. They split the affected section of software into smaller pieces, stored those pieces in different parts of the spacecraft's remaining memory, individually rewrote each piece to function correctly from its new location, and then carefully reconnected everything to work as a whole again. It was, in effect, remote brain surgery performed through a 44-hour communication delay on a machine pushing 50 years old, sitting farther away than any human tool has ever reached. In mid-2024, Voyager 1 came back online. Clean data, complete data. And what it immediately resumed sending back was more evidence of that same unexplained plasma hum in interstellar space, more measurements of a turbulent structure that no model had ever predicted. The spacecraft, that should have gone silent in 1981 and very nearly did go silent in 2023, came back from the edge with more secrets to tell us. Which brings us to right now, to 2026. Because this story is not finished, and the timeline left is shorter than most people realize. Earlier this year, NASA made a decision nobody on the mission team wanted to make. One of Voyager 1's scientific instruments, the low-energy charged particle experiment, which had been collecting data almost continuously since 1977, was switched off. Not because it broke. It was working perfectly. It was shut down because the spacecraft is running out of power and there simply wasn't enough left to keep it running. Voyager 1 gets its electricity from 3 radioisotope thermoelectric generators, essentially sealed containers of plutonium-238 that produce heat as the plutonium slowly decays, heat that gets converted into usable power. At launch, these generators produced roughly 470 watts. Today, nearly 49 years later, they produce around 250 watts, and they lose about 4 watts every single year. Sometime in the early 2030s, that output will fall below the minimum level needed to run any instrument at all, and Voyager 1 will go permanently silent. The team has known this was coming for years, and they've made a careful, painful plan for which instruments to shut down and in what order, trying to squeeze every last drop of scientific value out of a dwindling power supply. Of the 10 instrument packages Voyager 1 launched with, 7 have already gone dark. Each shutdown is one more set of questions that will never be answered, because there's no way to switch an instrument back on once you've decided you turned it off too soon. But here's the twist. Almost nobody outside the mission team is talking about they haven't given up on buying more time. NASA engineers are currently testing something referred to internally as a last resort power procedure, an experimental attempt to restructure how electricity flows across the spacecraft's remaining systems, squeezing extra capacity out of components currently running below their potential efficiency. It's risky. Rewiring the power logic of a nearly 50-year-old spacecraft with no way to manually intervene if something goes wrong could cause unpredictable failures. So they tested it first on Voyager 2, its twin, which has slightly more power margin and sits closer to Earth, making any failure less catastrophic. If those tests succeed, the same procedure gets attempted on Voyager 1 itself, and if it works, there's a real chance the recently shut down instrument could be switched back on. Nobody's promising anything, but nobody has given up either. And then there's the date, the one already locked into the calendar, arriving whether anyone is watching or not. On November 18th, 2026, Voyager 1 will reach a distance of exactly 1 light day from Earth. That means a radio signal moving at the fastest speed anything in the universe can travel will take a full 24 hours just to reach it. Send a command on a Monday morning, and you won't know if it arrived until Tuesday morning. You won't get a response back until Wednesday. 2 full days just to complete a single exchange. No object built by human hands has ever been that far away. Not once in the entire history of our species. It will cross that threshold while it is still alive. Still transmitting, still sending back pieces of a puzzle that grows stranger the more we solve it. But silence doesn't mean the end. Even after the last signal eventually comes, sometime in the early 2030s, Voyager 1 does not stop. There's nothing out there to stop it. No friction, no atmosphere, no gravity strong enough to meaningfully pull it off course. It will simply keep moving, silently, at roughly 38,000 miles an hour, into darkness with no, and on any timescale a human mind can really hold on to. And bolted to its frame is something that will outlast every part of the mission itself. The Voyager Golden Record. A gold-plated copper disc carrying greetings recorded in 55 human languages, the sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter, 90 minutes of music pulled from cultures across the span of human history, diagrams explaining the basic principles of our science and mathematics, and a map built from the positions of pulsars, showing exactly where in the galaxy our planet sits. Carl Sagan, who helped design it, once called it a message in a bottle cast into the cosmic ocean. That is precisely what it is. Whoever eventually finds it, whether that's another civilization millions of years from now, or some form of intelligence we can't currently imagine, the record will say something true, that a species existed here, that they were curious, that they reached, that they built a machine out of metal and mathematics, and launched it beyond everything they had ever known, carrying the sound of their own laughter with it. That record will still be drifting long after the sun swells into a red giant and swallows Earth's orbit. It will still be moving after every city, every archive, every stone we've ever carved a name into has been erased by time. It is, quite possibly, the single most permanent thing our civilization has ever made, and it is riding on a spacecraft, currently running on less power than the bulb above your kitchen stove. One fact in all of this is easy to lose, under the weight of the physics and the engineering, and it's the one worth sitting with. Right now, in 2026, the only functioning scientific instrument our species has ever placed in interstellar space is 48 years old. It was built using technology that predates the personal computer. It runs on less electricity than a household appliance. And it is sending back data that is forcing physicists to rewrite assumptions about the boundary that protects every living thing on this planet. We have built far bigger things since, far more powerful things. Things that cost exponentially more and use technology Voyager 1's engineers couldn't have dreamed of. None of them have told us what this machine is telling us right now, because none of them had the one thing Voyager 1 had. The sheer stubbornness to keep going long enough to actually get there. There are questions about the space beyond our solar system that can only be answered from inside it, not from a telescope on the ground, not from a satellite in Earth orbit, not from a mission to Mars, only from something that crossed the heliopause and kept transmitting on the other side. We have exactly one such machine, and it is old, and it is dying, and as long as it's still talking, we need to be listening, because when it finally goes quiet, whatever it hasn't told us yet may stay untold for a generation. There's currently no funded mission designed to reach interstellar space again. Even if one launched today, it wouldn't arrive at the heliopause for at least 25 years. The signal is still coming. Stretched across 15 billion miles, delayed by nearly a full day of travel time, describing a universe that is stranger, more turbulent, and more connected than any model built from the safety of Earth ever predicted. One machine, 4 watts, one window that is closing. Whether anyone's paying attention while it's still open is the real question left hanging. If this is the kind of story you come here for, subscribe and turn on notifications, because we're going deeper into the edges of what science actually knows next time. Drop a comment with the part of this that surprised you most, and share this with someone who needs to hear it, because a story like this deserves more than the silence it's getting. Thanks for watching.